In this video, we're going to talk about simplifying, adding, and subtracting radical expressions. Simplifying, adding, and subtracting radical expressions. There are times when we're going to have stuff under our radical that won't be perfect. Like it won't include a perfect square or a perfect cube or a perfect fourth. And so what we're going to have to do is learn methods to help us simplify that. All right. First thing I do when I simplify is I determine the index. The index is going to be very important because it's going to tell you whether you're going to be looking for perfect squares, perfect cubes, perfect fourths, so on and so forth. After I determine the index, I'm going to see if I have any constants. What I mean by constants are numbers, right? Well, if the number is perfect, then just go right ahead and take the root of that, right? Find whatever root you have depending on your index. If it is not perfect, we're going to determine if the radicand or that number has any factors that are perfect and rewrite as the perfect times another number, all right? After we do that, we're going to have two things on our radical from that one single number. We're going to have a perfect and another number. We just take the root of that perfect part and leave everything else under the radical. All right. The same thing is going to apply when we look at variables, right? If it is perfect, then, go ahead and find the root. If it is not, then we're going to rewrite that variable to an exponent as a product of two factors. All right. It's going to be the variable broken down into two other variables, or two variable expressions multiplied by each other, right? That's what factors mean. The exponent for the first factor should be the largest multiple of the radicand's index. That's why that index is very important in this first step here. And the radical's index that is less than or equal to the factor's original exponent. All right, that is a mouthful, and so it'll make a lot more sense when we look at an example. Let's look at a couple of examples. First example, and I'm going to try to leave these up here, these steps here. We want to simplify, and I'm just going to say that we're going to go ahead and assume that all of our variables are non-negative. We're not going to be worrying about that in this as we go over these. All right, we have the square root of 40, okay? You think about all your perfect squares or the number that you multiply by itself to give you 40, a whole number, there is not one. And so we need another method to simplify, and that's why this stuff comes into play. Well, in order for me to do that, what I'm going to do is I'm going to think about all of my perfect squares that could possibly go even into 40. Let's just list our perfect squares. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. Of course, we're not going to have anything go evenly into 40. That's larger than 40, all right? And so if I look at this list of perfect squares, right, these are our perfect squares, numbers to the second power, then I want to see which one of these numbers, or what's the largest number that goes evenly into this 40 right here that's in my radical, that's under my radical. And my answer would be 4. I can rewrite 40 as 4 times 10. All right? And this is the part where we rewrite as a perfect times another number. That's what I'm saying here. Write it as a perfect times another number. Now that we have the 4, well, since it is perfect, it does not belong under that radical. It's perfect, so it can go out. But when we go out, we have to actually take the square root. Right? The square root of 4 is 2. And so we end up with 2 times the square root of 10. Notice I am completely simplified because there is no perfect square here, all right, out of all these numbers here that can go evenly into 10. All right, and so this is completely simplified, and this is how we always want to leave our answer, completely simplified. So square root of 40 is the same thing as 2 times the square root of 10. Part B, we have the 5th root of x to the 23rd, all right? Now, what we normally say is we look at the index, right, which is 2, right? And we try to divide 5 evenly into 23, right? Well, 5 doesn't go evenly into 23. And so what we're going to do here is, and that means it's not a perfect 5th, right? That's the 5th root. It's not a perfect 5th. And so what we're going to do here is to simplify by rewriting this 5th root of x to the 23rd as the 5th root. All right, and we're going to do a product of two factors. A product of two factors. That's what I'm saying here. Rewrite it as a product of two factors. Product means multiplication. All right. It says the exponent on the first factor should be the largest multiple of the radical's index that is less than or equal to the factor's original exponent. My original exponent is sitting here, is 23. All right. Now I'm going to look at multiples of my index 5. Multiple of my index 5. 5, 10, 15, 20, 25, 30, 35, 40. The largest one that is less than or equal to 23 is 20. So I'm going to write this as x to the 20th power. And actually, this is x to the 23rd. I need 3 more, right? When you multiply and your bases are the same, you add your exponents. So I needed 3 more to get back to 23. So all I've done was rewritten this. I didn't change the problem. I rewrote it so that it'll look a little different. And now that this part right here is perfect, I can go ahead and take the 5th root of that. And so this is going to be equal to, well, 5 goes into 24 times. So I'm going to have x to the 4th. And then the 5th root, the x to the 3rd stays under my radical. All right. You know when you're done, when this exponent on your variable is less than your index. All right. Less than index. You're done. All right. So my solution is x to the 4th times the 5th root of x cubed. Other example. We have the cube root of the a to the 8th times b to the 15th times c to the 7th times d. All right. What I like to do when I have multiple variable expressions or multiple things under my radical, multiple factors, is I like to separate it and look at each individual thing one at a time. So I'm going to separate this. This is not a necessary thing to do. It just helps me in my thinking. All right, so instead of looking at everything all jumbled up together, I'm going to separate them. And notice, since I don't have an operation between this, it's still multiplication. Okay, my index is 3. And so I want to know what multiples of 3, right? Your multiples of 3, 3, 6, 9, 12, 15, 18. That's good enough for us, right? And so I want to rewrite these variables with their exponents as having one of these exponents and then another exponent that's out of the blue. All right. And so let's do that. All right. With 8, the largest multiple of 8 that's less than 3 is 6. So I'm going to have a to the 6th power. I need 2 more to get back to 8, right? 6 plus 2 is 8. So I have that. Times b to the 15th. Well, the largest multiple of 3, which is my index, that's less than or equal to 15, is 15, right? So this is actually perfect. I'm not going to take the perfect root yet. I'll come and take my perfect roots all at the same time. C to the 7th, well, my largest multiple of 3 that's less than 7, here we go, 6 again. So I have c to the 6th times c. All right, and the exponent on this d is actually 1, right? And so this is already simplified, right? So once this is less than, we know that it's already less than the index. It's completely simplified. So this is just going to stay d, all right? Now that I have this, I can go take my perfect roots, okay? Take the cube root of those perfect cubes, actually. And so, all right, we divide our exponent by our index. So I get 3 goes into 6 2 times. So I get an a squared times the cube root of a squared. Now this a squared is this one right here that's still under the radical. This one was the cube root of a to the 6th. The cube root of b to the 15th, 3 goes into 15 5 times. So I get b to the 5th. 3 goes into 6 2 times. So I get a c squared times the cube root of c. And then this is already simplified completely. I get the cube root of d. All right. Now we have multiplication. That means the order does not matter. So everything that's on the outside of my radical being multiplied, I'm going to write them together on the outside. So I'm going to have an a squared b to the 5th times c squared. And instead of writing these as one radical, since these will all be representing real numbers, I can write them under one radical being multiplied together. So I get a squared times c times d. And this is most simplified. Notice that all of my exponents under my radical are less than my index 3. All right. I'm going to look at one more example of this. We have the cube root of 378, x to the 20th, y to the 10th, z to the 6th, w squared. All right, we're going to do the exact same thing here. I'm going to separate these. It's 378, cube root of 378, times the cube root of x to the 20th, times the cube root of y to the 10th, times the cube root of z to the 6th, times the cube root of w squared. Okay, now we were talking about perfect cubes here, and I have a number here. I want to remind myself of all of my perfect cubes. 2 cubed is 8, 3 cubed is 27, 4 cubed 64, 5 cubed 125, 6 cubed 216, 7 cubed 343, 8 cubed 512, right? And so to simplify this, I want to find the largest perfect cube that goes evenly into 378, all right? And so if you think about it, pretty long, you can get your calculator. This is one where you probably want to get your calculator. But you'll find that 27 times 14 will give you 378. And so I'm going to write this as the cube root of 27 times 14. Okay? And now the variables are going to be the exact same thing as before. We're looking at multiples of 3, all right? Multiples of 3 are 3, 6, 9, 12, 15, 18, 21. I think that's enough, right? So the largest multiple of 20, that's 3 that's less than 20 is 18. So I can write that as x to the 18th times x squared. For y to the 10th, you can write it as y to the 9th times y. Z to the 6th, 6 is a perfect cube, so I'm going to leave it the same. And the index on that w is less than the exponent on the variable w is less than my index, so that is already simplified completely. Notice we have a lot of perfect cubes here. There's one there, there's one there, one there, and one there. They don't belong under the radical, so that means we can simplify them. The cube root of 27 is 3. Still going to be left with the cube root of 14. The cube root of x to the 18th, 3 goes into 18 6 times. So I have x to the 6th times the cube root of x squared. The cube root of y to the 9th, 3 goes into 9 3 times. Still have that cube root of y under my radical. 3 goes into 6 2 times. So I get z squared. And I still have my cube root of w squared. Now that I have these, everything that's on the outside of my radical is going to stay on the outside of my radical. And everything on the inside of my radical is going to be multiplied together. So I have a 3x to the 6th, y to the 3rd, times z squared. And I'm going to multiply that by the cube root of 14 x squared y w squared. All right? And so that's the gist of simplifying, right? And you know, at the end, if you can't take a cube, and there's no factors that can have a cube in it under your radical, your index is smaller than your index, your exponents are smaller than your index, then you know you're done. This leads us to being able to add and subtract radical expressions, okay? And so we know how to simplify radical expressions. We know about radical functions. We know about the domain of radical functions from previous lessons. And now we can get to adding, subtracting, multiplying, and dividing radical expressions so that we can eventually solve radical equations. Well, adding and subtracting radical expressions involves basically combining like terms, all right? And what I mean by like terms, you might hear someone say like radicals. All right? And what I mean by like radicals is, you know, they have to have the same radical, right? For instance, 2 times the square root of 2 and negative 7 times the square root of 2. Those are like radicals, all right? So these work well. But, an example like this, 2 square root of 3 and 3 times the square root of 2, they're not like radicals because we have a square root of 3 and a square root of 2, and those would not be considered like radicals, all right? And so sometimes before we actually can get to combining, we need to simplify first. So my first step in adding and subtracting radical expressions is to simplify all of my radicals if possible. And after I'm done with that, I'm going to combine my like terms, combine my like radicals, which is the same as combining like terms from before. Let's look at a couple of examples. I have 9 square roots of 2 plus 5 fourth roots of 3 minus 14 square roots of 2 minus 2 fourth roots of 3. All right. If I look at the square root of 2, it is already simplified. And the fourth root of 3, that is already simplified. And I see it there and there. So I don't have to actually do this first step, which is given right here. All I have to do is simplify or combine like terms. Sorry. All right. 9 square roots of 2 combines with negative 14 square roots of 2. Right? My square roots of 2 are going to stay the same. All I have to do is worry about adding or combining the coefficients. I have 9 minus 14, which is negative 5 square root of 2. My other like terms are the 5 fourth roots of 3 and the negative 2 fourth roots of 3. Again, we look at the coefficients out front. We got a 5 and a negative 2. That'll be plus 3 times the fourth root of 3. And this is completely simplified. I can't combine anything else because I have no like terms. I have no like radicals. Let's look at another example. All right, I have 7 times the fifth root of x squared plus 14 times the fifth root of x to the 7th. And I want to simplify completely. Maybe even add and subtract. Well, if I look at this example, when I look at the fifth root of x squared, all right, that is already simplified. That 2 on the exponent under the radical is smaller than our index. However, when I get here, the 7 is bigger than that 5, index 5. So what I'm going to have to do is I'm going to have to simplify that fifth root of x to the 7th. This would be 7 times the fifth root of x squared plus 14. If you think about multiples of 5, 5 is the smallest one that's less than 7. So I can rewrite x to the 7th as x to the 5th times x squared. Since I now have this being perfect, I can take the perfect root of it. I'm going to leave my 7 times the 5th root of x squared the same. But 5 divided by 5 is 1, so when I take the 5th root of x to the 5th, I'm just going to have x. And under my radical remains the x squared. And so now, if I look, this is what the radical, this is the radical that I have. And if I look here, this is the radical that I have. And so you might think that you might be able to combine like terms. But I have a variable here. I don't have a variable out front here. That means I can't combine like terms, and I'm done with this problem here. So although we simplified, we actually couldn't add these together because they're not like terms. They have to not only have the same radicals, but if there's a variable on the outside, they have to have the same variables as well. Now, if there was a x in front of that 7, or after that 7, then we know that we can add 7x and 14x, and that would have given us 21x times the fifth root of x squared. But that wasn't the case in this example. All right, one more example. We have the square root of 90 minus 4 times the square root of 45 plus 3 times the square root of 250 plus 8 times the square root of 80. And we want to simplify, okay, or add or subtract. Well, if I look at the square root of 90, I actually can simplify that a little bit. Before I start simplifying, I'm going to write down our list of perfect squares, right? 2 squared is 4, 3 squared is 9, 4 squared is 16. Get 25, 36, 49, 64, 81, 100, 121, 144, 169, so on and so forth. All right. I think we have enough here. I was going to go to 200 something, but that would require us to go to past 15 or whatever. But if I look on this list here, of course, 90 doesn't go past 81, right? If we look on this list of perfect squares, the small or the largest one that goes evenly into 90 is 9. Okay? And so I can rewrite 90 as 9 times 10. Now I'm going to go to the square root of 45. If I look at 45, the largest perfect square that's less than or that goes evenly into 45 is 9 as well. That would be 9 times 5. Square root of 250, all right? If I look at 250, the largest perfect square that goes evenly into 250 would be that 25 sitting there. 25 times 10. And for 80, the largest perfect square that goes evenly into 80, all right, you might think 4, but it's actually going to be 16. 16 times 5 is 80. And so now I have some perfect stuff under my radical. These things are perfect squares under my radical. And so I am actually going to simplify by taking the square root of these things. So I get 3 times the square root of 10 minus, I have a 4 on the outside. When I take the square root of 9, that's 3. So I've got to multiply that 4 by that 3, and the 5 stays under my radical. 25, I can take the square root of that, so I have 3 times 5 times the square root of 10. And 8 is going to be multiplied by the square root of 16, which is 4, and I still have the square root of 5. And of course, we can simplify that even further. That'll be minus 12 times the square root of 5 plus 15 times the square root of 10 plus 32 times the square root of 5. And now this looks a lot simpler. So at first it looked like we couldn't combine like terms because they weren't the same, but as we simplify the radicals, we found that we can actually combine like terms. All right. These are our sets of like terms. They have the same radical. So I'm going to combine them. All right, 3 plus 15 is 18. So I get 18 times the square root of 10. And a negative 12 plus 32 is positive 20. And I still have the square root of 5. All right, and so this is how far I can go. And this concludes our lesson on simplifying, adding, and subtracting radicals.